In the last lecture, we saw how we could use Kirchhoff's current law to calculate currents in a circuit. The example circuit we analyzed was very easy to compute because we knew the node voltages. But that won't always be the case. Moreover, we kind of did all of those calculations in a haphazard way. In this lecture, we will address those issues by using what's known as nodal analysis. Nodal analysis is basically the same thing as we did in the previous lecture, but it's represented in a more structured step-by-step process. Nodal analysis is very powerful because it works for any circuit and can answer anything you might ask about a circuit or circuit component. So, what's the strategy of nodal analysis? Well, if we want to know anything about a circuit, we need to know all the voltages and currents. In fact, if you just know all the node voltages, you can compute the currents as well. So all you got to do is figure out the node voltages using KCL equations. And from there on, you can calculate anything else that is asked for. That's the strategy. And these are the steps to calculate the node voltages. First, we need to identify all the nodes and label them from 0 to n, with the ground node being the node 0. After that, we will work with the voltage sources. Then we'll use the Ohm's law to get the current through each resistor. Once we get all the currents, we can write KCL equations. And lastly, we will solve all the equations. You can either use a calculator or online equation solver to do this. Okay, so this seems more complicated than it really is. So let's walk through an example. This circuit is almost similar to the last one, but with a current source on the right instead of a voltage source. Let's use nodal analysis on this circuit. Step 1, as the name suggests, first you have to identify all the nodes. Here we have 3 nodes in total. So we numbered them from 0 to 2, with ground node being the 0th node. And remember, every node has one voltage associated with it. So we name the voltages as V0, V1, and V2. Now by definition, ground has 0 volts, which means V0 is just 0 volt. So we know the ground node voltage by default. That's why often we don't even bother with the ground node and label it as the 0th node. The main players of this circuit will be V1 and V2. Believe it or not, if you can figure out just these two numbers, you can tell anything about this circuit, like how much current or power is any of the resistors drawing and how much power is being supplied by each of the voltage or current sources, etc. Okay, so let's move on to the next step. We have to write the component equations for every voltage source in the circuit. Here we have only one voltage source with 1.5 volt voltage difference. Its positive terminal has a voltage of V1 and the negative terminal has a voltage of 0 volts. So the component equation for this voltage source will be V1 minus 0 equals 1.5, which just translates to V1 being 1.5 volts. Always remember, voltage difference should always be calculated as positive terminal voltage minus negative terminal voltage. So we already solved one of the node voltages. Since we already knew the voltage of one side was 0 volt, it was really easy to compute the other side as well. So that concludes our second step. Next, we have to figure out the current through resistors in terms of node voltages. And Ohm's law will help us do that. Let's give some names for these currents. I'm just taking directions arbitrarily. It doesn't matter which direction you take as long as you follow passive sign convention. Now, let's take a closer look at the resistors one at a time. We know from Ohm's law that the current is equal to voltage difference divided by resistance. But make sure you label the positive and negative terminals following passive sign convention. The current must flow from positive to negative terminal. Now we can use Ohm's law to express I4 in terms of node voltages. Again, keep in mind that the voltage difference should be calculated as positive terminal voltage minus negative terminal voltage. Okay, we are done with this resistor. Let's move on to the next resistors. Let's do the exact same things for the remaining resistors. And now step 3 is complete. Since we know the currents, we are now ready to write KCL equations. That's the next step. You'll see I mentioned you don't need to write KCL equations for nodes whose voltage we already figured out. For example, we already figured out node 1 has a voltage of 1.5 volts. So we don't need to write KCL equation for node 1. In fact, even if you try to, you'd get in trouble. Let's try to write KCL equation for node 1 anyway. Reminder, KCL equation just says total current entering and exiting the node should be same. And I also said that I will write everything on one side of the equation. So if current is exiting the node, I add it, and if a current is entering the node, we subtract it. Let's try it on node 1. We have I2 exiting the node, so we add it. 0.5 amperes is also exiting the node, so we add it as well. I4 is entering the node, so we subtract I4. Now what about the voltage source? We don't know what this current is. And if you remember, in the last lecture, this is exactly where we got stuck because the component equation of a voltage source says nothing about current. We have run into some issues here. That's why I mentioned we don't need to write KCL equation for node 1. And why bother anyway? We already know the voltage of that one, so we can just skip them. But we still have to write KCL equations for the remaining nodes. So let's do that for node 2. We have I4 and I5 going out of the node, so we add them. The 2 ampere current is also going out, so we add that as well. And lastly, we have 0.5 amperes of current entering the node, so we subtract that to get the full KCL equation. Now, we still need to express everything in this equation in terms of only V1 and V2, because our target is to find V1 and V2 and figure out everything else from that. So we substitute the values of I4 and I5 and do some manipulations to get an equation purely made up of V1 and V2. This last equation is our final product. By the way, take a look at this equation along with the original circuit. See if you can find a pattern. If you can find the pattern, you could write this final equation skipping step 3 entirely and even the equation manipulating parts of step 4. For now, let's move on to step 5. So right now we have 2 equations and 2 unknowns. So we could easily solve the equation by using a calculator or an online linear equation solver. For this particular circuit, we already know 1 voltage. So just by substituting 1.5 for V1 in the equation for node 2, we will get a value of negative 3.86 volts for V2. And now that we know all the node voltages, we can answer any questions thrown at us. For example, if I ask you what's the current flowing through this 4 ohm resistor, you could just use the equation for I5 and get negative 0.965 amperes of current in the designated direction. By the way, because we get a negative current, it just means in reality the current is flowing in the opposite direction. But that's beside the point. Usually in questions, you will be asked the values of current in a specific direction. So that way we will have no ambiguity about the value of current. What else can you calculate from just the node voltages? Well, you can calculate the currents through any resistor just like the 4 ohm resistor. But you can do more. What if I asked you how much power is consumed by 10 ohm resistor? To answer this question, we need to remind ourselves of the equation for power through resistors. We can use any of them and you will get the same answer either way. I'm going to use the last one. Remember to use passive sign convention. So we get 2.87 watts. Remember, positive power for a component means it's consuming or drawing power from the circuit. Resistors always consume power, so it is as expected. Okay, so we can calculate powers consumed by each of the resistors. Can you do the same for the sources? For example, can we calculate how much power this current source is drawing or supplying to the circuit? Yes, we can. Following the passive sign convention, the positive and negative terminals will be like this. Now, we can use the general formula for calculating power. And as we can see, the power we get is negative, which means the current source is supplying power to the circuit. So now we can calculate the power for current sources as well. And now, lastly, we can calculate the power of a voltage source. Let's see how we can do that. Since we have positive terminal on the top, and according to the passive sign convention, we need to take the direction of current from top to bottom. And this is where we ran into this same problem. In order to figure out the power, we need to figure out the current first. Unfortunately, we used to get stuck here, but not anymore. Because now we know all other currents. As we did in the last lecture, we can now use KCL equation of node 1 to figure out this current. So we get a negative 1.486 amperes for this current. And from that, we can calculate the power as well. I think I have proved my point that from just these two node voltages, you can calculate anything asked about this circuit. I hope you can see how powerful this nodal analysis method really is. Now, there's two things I did not discuss. Number one, I mentioned that if you can find a pattern, you can skip step 3 and 4. So what's that shortcut? And number two, in step 4, I mentioned something called supernodes, which I did not discuss. Let's walk through another example and discuss these two issues.